Okay, then. All right. So we have all of the tools that we need to deal with exponential and log equations. Today, I just wanted to take a look at a couple of application problems, places where we see exponentials actually come up in kind of real world, situations. We're going to start with kind of revisiting the compound interest thing again. Logs as models for things, there aren't a lot of, I can't count. Logs as models don't come up in that many places. When they do, it's kind of, forced a little bit. Things like Richter scale, like earthquake intensity, that's a log scale. Decibels, sound intensity, that's also a log scale. So like you can, kind of do that a little bit, but like, I don't know, it feels a little bit odd to me generally. So these are mostly going to be exponentials, but that means that we'll use logs to solve them. So first, the compound interest formulas. Again, those two formulas are printed on the test. So you don't need to, sorry, if you need them. In the hypothetical situation that you need those, they're provided. But you need to know which one to use when and what everything represents, of course. So suppose you invested $1,000 in an account paying 3% interest compounded continuously. How long would it take for that investment to grow to $1,200? How would we set that up? Okay, pick the right formula. Then what? Plug everything in. Okay, what's everything? All right, so A is PE to the RT. A is the amount after some time passes, right? So thinking of this as like a function of time, A of T, if you want. That's amount now, amount at time T. P is the principal or the starting amount. E is the, R is the interest rate, T is the time in years. What's the question asking? How long? So what are we not going to know then? T. We're going to need to solve for T. If the thing I need to solve for is T, that means that somewhere in the problem I have everything else because we only know how to solve for one unknown, right? We can't handle two variables right now. So you invested $1,000 in an account at 3% interest compounded continuously. How long would it take for it to grow to 1,200? Interest rate. These are your two amounts. Which one's which? That's the principal. This is the A value then, right? The value after time. So 1,200 equals 1,000. E to the 3%, so 0.03. And then again, T, I don't know. Solving for T, so T. Take a minute and solve that. Okay. Okay, so what's first to solve this? Divide by 1,000. Yep. The thing we're solving for is right there in the exponent. So the first thing we need to do then is get that term by itself. Divide both sides by 1,000 to move that away. 1,200 divided by 1,000, that's 1.2, right? Now I'm not rounding. You can leave it as 1,200 over 1,000. You can write it as 12 over 10. You can reduce it to 6 over 5 if you want. You can write it as 1.2. What you should not do is round in the middle of the problem though, okay? Because often, if you round in the middle of the problem, even if you're doing the right things, by the time you work all the way down to the end, it's going to be wrong. On stuff I'm grading on paper, that's not as big a deal as long as I can follow what you're doing. But of course, for like online stuff, it's just going to, count it wrong and you might not really see why. But always be careful about rounding in the middle of stuff. Again, I'm not rounding here. This is exactly 1.2. Okay. All I'm going to do is sort of push it around for a minute and then punch it into a calculator anyway, right? So if you want to just leave it as 1,200 over 1,000, there's nothing wrong with that. Now what? Solving for this, it's in a power on this exponential with base e term. So log, right? Rewrite it as a log. The base is e, so natural log makes sense. If I take the ln to both sides, what happens on the right? Yep, and we just get 0.03 t. The natural log of 1.2 is just some number, right? It's messy, it's some decimal thing if I try to like use a calculator to find it, but it's just some number. So I've got 0.03 times t is equal to some other number. How do I solve for t then? Divide. Divide by 0.03. So t is whatever the natural log of 1.2 divided by 0.03 is 6.077. Most of these, most of the stuff you're going to see is going to ask you to round to like a 10th of a year. So I'm going to write that as 6.1. And that's just this, right? Punch that into the calculator and got 6.1 or something that rounds to 6.1. Okay. Everybody all right with that? For the most part, once you get the setup done, just about any of these that you're going to see are the actual like solving part is going to feel a lot like this. Like you're just going to end up doing kind of the same sort of thing to solve them. We've got a power E, an unknown power B that we don't know that we're looking for. Well, do the opposite thing, which is a natural log. Maybe you have to do some stuff beforehand. Maybe you have to do some stuff on the back end to finish it out, but the natural log ends up being kind of the key step. All right, I'll take a minute and think through how you'd set up number 2. Okay, so what feels different about this one? I didn't give you concrete values, like I didn't give you a number, right? Because I'm asking about how long it would take for any investment to double. Okay, so what did I give you that's, sort of like, concrete?
3%.
The interest rate, 3%, compounded continuously, so we know which formula we're using. The question is how long? So we're looking for T, right? Okay, so continuously, so we're using this. So A is PE to the interest rate 3%, trying to find T. But what I didn't give you are values for these. So how do we deal with that? Okay, pick one, pick what?
I did 5
For
E and then
for P, okay,
2 times 5 for A.
okay. Grady had $5 in his pocket and said, hey, I'm gonna go put this in the bank and see how long it takes for it to turn into $10. Can we do that? What would be the first thing we would do to solve this? Divide by 5. When you divide by 5, what do you get? 2 equals E to the 0.0, I forgot how to make it 3, 0.03 T. Hey, if I chosen a different amount here, somebody else throw out a number. 100. If I chose 100 here, what would need to go here?
200.
Double, right? 200. What would be the first thing I'd do to solve that? Divide it over. What would I get right here? Because that's the relationship, right? The thing about exponentials is that the exponential handles the growing part, the change, right? When you multiply, what you're doing is saying, okay, well, you start with this amount, and you're multiplying by how much growth has happened, right? So what we're asking here ultimately turns into, hey, how long is it going to take for that exponential to be the same thing as just multiplying by 2, right? So whatever value I chose here, as long as this is really double that, right? So times 2 to get this, then you're going to end up back here anyway, right? Which is, by the way, there's kind of an implied 1 here, right? This is like me saying, hey, how long does it take for $1 to turn into $2? It's like I can still think of this, even when I don't need to like write the p-value. I can still think of this as doubling for a like concrete example. So we don't have amounts, but it's because we don't need specific amounts. We just need the relationship to be preserved, right? So if I said the same thing and said, how long would it take for an investment to, I don't know, triple? Well, you do the same kind of thing. This would need to be 3 then instead of 2, right? Everybody okay with that? So if you're more comfortable with it being, a little more like concrete, then pick a number here and this one needs to be double, right? So you choose P and then A is 2P because we're talking about doubling, and then solve. If you're okay with the idea that well, double means times 2, and you can just sort of jump to right here, then that's fine too. How would you solve from there? Take a natural log, then divide over by 0.03, sorry. So the solving part here is going to look just like the solving part here, right? The rest of the stuff that we need to do is going to go almost exactly the same as what we just did. Natural log of 2 is 0.03 T. So T is the log of 2 divided by 0.03. $23.1 years. which is a long time, right? But start saving now, kids. Yeah, there you go. Okay, question about that? Okay. So yeah, this is one, and we'll see a couple more today too, where you read it the first time and you're like, that's not like you didn't tell me everything, right? It feels like you don't have enough information, but we do. We just have to fill in some blanks a little bit in what's going on. Okay, 3 should be a little bit more concrete. So why don't you guys take a couple minutes and set up and try to work through what's going on in 3.
Set it the same.
Mm-hmm. There's 2 things you're comparing, so you're basically going to need to set up and work through them separately, and then compare the answers. Okay, so we've got these 2 separate things that we're comparing. The question is when, right? So we're going to be looking for T, right? So we should have everything to set up the formulas except for the T value. So for this first option, 1.7% interest compounded quarterly. We're starting with 2,500 and we need to save up to 3,000. So what does the setup look like there? 3,000 equals 2,500. .017 over 4 because it's quarterly to the 4T. $2,500 principal. That's how much I have now. I want to figure out how long it's going to take for that to grow to 3,000. So there you go. 1 plus interest rates 1.7. So slide the decimal over 2 places, 0.017. Quarterly. So it is for, and we're looking for T. Okay. What about the other one? .014, because the interest rate's different. T. Yeah, good. Okay. How are we going to solve those? They look different, right? Because one's using one formula, the other's using the other. What's actually different in the two things, though? Like structurally, or that affects how we're going to go about this. What do we need to do? Where is the thing that we don't know, the thing we're solving for? T, where is it? In the exponent. So what are we going to need to do? A log at some point, right? I'm going to need to get the term with the exponent by itself and take a log, and then maybe move some stuff around at the end to get t by itself. It's t times something, so I'm going to have to divide at some point. Okay. So where should we start? And I don't want to have to keep writing this thing, so I'm going to go ahead and simplify that to it's 0.00425
Plus 1.
Yeah, right. To the 4t. Okay. And again, none of that is rounded, right? We just found the decimal version. Okay. Now what? Take a log, right? This looks a little bit worse because the base is this messy decimal thing, right? But like push past that, right? It looks a little bit worse because of this, but what we're looking at is exponential thing with a power that I want to know about is equal to some number. Well, I need a log then, right? Because logs tell me about the missing power. So how do you want to do that? Use that as the base?
Oh, yeah.
Or, sorry, is that what you were saying? Or
Yeah.
okay.
What are we doing for 1.2?
Okay, so look at it this way. This is the, answer, right?
Yeah.
Base, exponent. So if I rewrite this as a log, it's the log of 1.2. It is equal to 4t. And then divide by 4. It's not like you were going to do this log in your head anyway. You have to punch it into a calculator. The calculator doesn't care what the base is, right? So we take that log and get whatever, it's 10 something, I think. Does anybody have it? If you're not super comfortable with, rewriting it as a log with that, messy base, if using 1.0045 as the base for the log makes you, queasy, then you could instead just like take the log of both sides, right? Use common log, use natural log of both sides and just move stuff around and you end up at the same place anyway. So it doesn't really matter how you do that. 10.7, okay, years. So probably not really a viable plan for how you're gonna save up the down payment on this car. But again, this is like, I just put the money in the bank and let it sit, right? So, okay, there's that. Now, fundamentally, the solving for the continuous interest one is gonna be exactly the same. We're gonna do all the same stuff. The base is E there. So that part's a little more compact, right? E doesn't look as scary as 1.00425, hopefully. And then when I take a log, I'm gonna take a log base E, which is a natural log. So again, it all just like looks a little bit cleaner, even though we're doing all the same stuff. So I'm gonna divide by 2,500. That's still 1.2. But then I'm gonna rewrite using a natural log. And divide log 1.2 over 0.014 to get, it's like 13 something. 13. Okay, so which one should we choose? This, but I'm still not super psyched about it, right? I'm probably not gonna need $3,000 for the down payment on the car in a decade. For the same car, right? Okay. So we're getting a feel for, I mean, one, the setup, and two, like how the solving goes. You see how like the solving stuff, like we're just kind of doing the same thing over and over again. Yeah, okay. All right. Let's take a look at another example, another place where this comes up. Radioactive decay. So the thing that makes radioactive stuff radioactive is that the way that the atoms and molecules and stuff are bonded is unstable. So they break down. When they break down, it shoots off little subatomic particles all around. And those are the things that, I mean, one that we use for useful stuff like generating electricity or, X-rays or microwaves or whatever. But two, if you stand too close to it for too long, weird stuff happens to you and you get cancer and things like that, right? So the thing that makes stuff radioactive is this instability. Because of that, it decays over time and degrades over time. And that's how we do things like carbon date. Like that's how, archaeologists or whatever can, look at ruins in Rome or whatever and figure out this thing is, however long. It's by measuring the amount of certain radioactive isotopes that are kind of everywhere and figuring out, how much ought to have been there and how much is there now, kind of. The terminology, the like common, metric for that is the half-life. Half-life is the amount of time it takes for something to decay by half. So if I take a lump of, some radioactive thing and just set it in the middle of this room and leave it alone for, 10,000 years or whatever, after its half-life has gone by, there will be only half as much of it, remaining, right? And the other half will have broken down to, become more stable and not radioactive anymore. So the half-life is the amount of time to for a radioactive substance to decay. Wish I'd made this a longer, wordier sentence. To half of the original amount. Okay. And please don't go give a like word for word retelling of that explanation of half-life to your chemistry professor or something, because like it was probably not perfect, but general idea. That's enough to get us by. Okay, so if a half-life goes by, say the half-life's 30 years, if I come back and check on it in 30 years, there's only half as much of that radioactive isotope left. This is the model that we use for exponential decay. AFT is this is a subscript 0. So A0 or A naught is the way people read that often. Anytime you see a subscript 0 like that, it almost always means starting amount or what happens at time 0. E to the KT. Does this look familiar? Yeah. And there's a reason it looks familiar. It's exactly the same model, just with different labels because it's talking about a different context, right? It doesn't make sense to talk about the principal amount of, uranium-238 or something. Instead, we talk about the initial amount, so we label it differently. So A of T, well, okay, I'm just thinking of the amount as a function of time, right? So this is function parentheses. We did that same thing here pretty often. We just didn't write it the same way, maybe. But that's the amount after some time passed. That's given by, well, P and A0 or A0 do the same thing. So that's the starting or the initial amount. E is E, T is still time in years. That means that this K does what R did, right? It's not an interest rate, right? It's not that the bank says I get 3% interest. It's still a growth rate though. So this K value works like a growth or an interest rate. It's something that depends on what kind of material we're talking about, right? Certain radioactive isotopes, are different than others. That's why some are, more dangerous than others and used for different things and whatever. So that K value, that depends on the material. But once we've kind of figured out, that this is really just this, it should make life a lot easier for how we work with these. This is another place though, where you read the question and it kind of feels like we don't have all the information we need, right? So the half-life of carbon-14 and the 14 part, that's just the name of the thing. It's like how many neutrons are in the atom or something. I don't remember. Chemistry was a long time ago. But the half-life of carbon-14, again, just the name, is 5,730 years. And that's all we're told. So similar to like the doubling thing, I didn't give you any specific amounts. I told you the only like specific concrete number we have is that would be a T value, right? Because it's time. But we don't have any set amounts, and we also don't have a value for K, right? What I want you to do is find the exponential decay model. So what can we set up with what we do have? That's T, right? Okay. So A naught, I'm going to erase those and fill something in. We don't know K. We know that T is 5730. That's way too many things to solve for though, right? I can't deal with 3 unknowns. That means that somehow we must have enough information to fill these in. How could we do that? If the half-life is 5,730 years, then after that much time has passed, what should have happened? Divides by 2. You got half as much left. Okay. Give me a starting amount. Okay. 2 works. After 5,730, after 1 half-life passes, how much should be left from that original sample of 2, grams or whatever? Half as much. A needs to be half of A naught. Because again, what's the very first thing we're going to do to solve this? Divide by 2 and get 1/2 equals e to the 5,730 K. So the question is really, when is the exponential thing the same as multiplied by 1/2, right? Just like the doubling problem with the interest, that's growing. So I can talk about how long it takes to doubling and set it up the same way. This is decaying, so it's got to be working the other direction. But apart from that, it's the same idea. This is half of that. And it wouldn't matter what you chose to be your starting amount. as long as I took this to be half of that, because the first thing I would do is divide it over anyway and get something that reduces to a half, because that's the relationship between those two numbers that we're supposed to be like preserving. Okay. What is solving from there going to look like? Natural log. So log of a half divided by 5730. Say again? Oh, yes, okay, hang on. So did you get something like this? Yes, okay. This part is scientific notation. So this means the same thing as that, which means that you take the decimal and slide it 1, 2, 3, 4 places to the left, and then fill in zeros. So this is negative 0.123121. Yeah, that's a small enough number, and you know your calculators and stuff are programmed so that if it's got a bunch of leading zeros like that, it doesn't display them usually. So if you get something like this, that means scientific notation. So you slide it over 1, 2, 3, 4 places and fill in zeros. That means this has 3 leading zeros. So that K value is negative 0.123 zeros and then 1 to 1. Because this thing is decaying, that K value always will end up being positive. This is a place where, like, depending on where you look, sometimes the formula will be written like that, where the negative is like built into the formula, right? But the point is that E is bigger than 1. So E is growing normally, right? We need to make it decay. Well, the way you make it decay is by reflecting, by making that exponent negative, so that, you know, in some sense, the base is like 1 over E, right? But that constant, the exponent there, you know, you've got K and T. T is time. That has to be positive. K has to be negative then, in order to make that whole thing negative. So K is a growth rate constant thing. So it works like the interest rate, but it's not like a percentage, right? So it depends on the material. So like that's the K value for carbon 14, because that is actually the half-life for carbon 14. I looked it up. For a different radioactive isotope, K is going to be something different because it's like tied to that particular material and how it works. Okay. Okay. Right. Yeah. So like if you were, you know, a working archaeologist or whatever, like K is a thing that, you know, you would either know for the material that you're using to do your carbon dating or your radioactive dating, or it's a thing that you would like go Google, right? Or look up. But it's a thing that's tied to the specific material. Okay, so the exponential decay model for carbon 14 then, A of T is A naught E to the negative 0.12321 T. And then that's what you're going to use to answer the next two parts. Basically what we just did, if you want to tie it back to the interest problems again, basically what we just did is find the R value. And now we're just plugging in and answering, you know, other questions. Here you're looking for how long, so you're going to plug in and find a T. Here you're looking how much of a sample is left after 500 years. You're going to plug in and have everything to just, you know, basically use the formula to find A. But that first part, the, you know, finding the model where it feels like, you know, you read the problem and all the information's not there. That's the part that I wanted to particularly talk about, because the half-life thing is telling you how to find the amounts. Okay. questions about that? Okay. One more quick example. Newton's law of cooling or Newton's law of warming. Basically, this governs how temperature of an object changes, right? So I bring my hot cup of tea in at the beginning of class and I set it down and the temperature in the room is lower, so it cools down, right? This formula looks a little more complicated because it's got more moving pieces, but capital T's, and there are, you know, 3 of them. Capital T's are temperatures. Little t is time in minutes now instead of years, but I guess years would be a weird unit of time for the temperature of my cup of tea. So t is still time in minutes. Capital T is temperature. So this is temperature after some time passes, right? Like temperature now, that kind of thing. T's with a subscript 0, T naught, that still means starting or initial, right? So that's how hot my tea was when I brought it into the room and set it down. The other one here is this T with an A subscript. We take the difference in those two things here, and then we've got, again, like an exponential term. It's we're talking about a thing that's cooling off, so the temperature is decaying. That's why this is negative. R is, again, some kind of rate thing, right? It depends on the material. Like my cup of tea is different than, I don't know, molten steel or something, right? So it's some kind of thing that depends on the material. But this is the part that's doing the cooling. What does this do? Plus T sub A. What does that do to the function or the graph? Shifts it. Which way? Up, right? I'm adding something on, you know, at the end, right? Outside of the function, that shifts it up. Well, for an exponential, that means that shifts the horizontal asymptote from 0 up to whatever that is, right? So what does TA do then? That's where the asymptote is now, right? And we're talking about this thing that's cooling off. The function, the graph is the temperature, right? If I bring my tea in and set it in the room and leave it, you know, all day and come back, how much is that going to have cooled off? To room temp, right? It's not going to like sit there and freeze. It's not going to get to absolute 0 if I leave it alone long enough, right? It's just going to cool down to the room temperature. That's what this is. The A is for ambient, you know, because we got to be fancy, but that's just the room temperature. That's all that is. So that plus T sub A at the end, it just shifts that horizontal asymptote up because that's as far down as it's going to cool, right? And at some point, it's close enough that I can't measure the difference anymore. So, you know, that's how much it cools down. That's also why here we take the difference in the initial temperature and the room temperature, right? There's a big difference in me setting my hot cup of tea in this room versus inside a meat locker or inside a sauna or something, right? If I put it in a cold room, well, that's going to affect how it cools down. If I put it in a hot room, it's going to affect how it cools down. So that's why you have the difference in those two things there.
So that's a good formula for heat transfer.
Yeah.
Wow.
Yeah. Now, I mean, so obviously, like, depending on what you're doing with it, right, things can get more complicated than that, right? But yes, this is how that model works. Okay, so if we take a pizza that is 100 degrees to begin with and set it in a 75-degree room, if the pizza cools to 100 degrees after 10 minutes, how long will it take? So our final answer is going to be how long, right? Little t,
Yeah.
to cool to 90 degrees.
So it's going to be 150 minus 75.
150 minus 75.
Then times E, the RT.
Yep.
T is going to be like the last value, T of A is going to be like,
Okay.
or wait, no, it's not.
No, you're right. You're right.
Oh.
To get our final answer, we're going to be looking for this t, right?
Yeah.
What's the problem?
So we can simplify.
How many variables does this thing have in it? Or how many unknowns? Things we don't know. Two. You know how to solve for two things you don't know? Simplify. Nope. So what do we need to do first? What's the other thing we don't know there? I know I need to find T, like that's gonna be my final answer. That's how I answer the question, is finding that little T that's highlighted.
Oh,
I gotta find R first, though.
is it 10?
To find R, what's the other thing the problem tells us? It's 100 degrees after 10 minutes.
50.
So when little t, temperature or time is 10, the temperature of the pizza is 100. I can find R there. Once I find R there, I can plug it in here and then find T, right? Now, look at what you're gonna have to do to actually solve those. 150 minus 75, go ahead and combine those. Subtract the 75 over. So this is 75 e to the negative 10r. I'm going to subtract 75. This one. Then I'm going to divide by that. And then take a log. So R is whatever the log of one, natural log of 1/3 divided by negative 10 is. I'm going to take that value and substitute it in here. But the actual solving part of this is going to be step for step exactly the same thing that you did here, but with different numbers, right? Like you're going to do the exact same thing because you're solving for something that's in, essentially the same place. So you'll have R and you'll be looking for T now. You got 90 on the other side instead of 100. But apart from that, it's going to be step for step, do the exact same stuff to find T. And we should have a decent idea about like a guess for an answer, to check ourselves. It took 10 minutes to cool to 100 degrees. So how long to cool to 90? It's cooling down, so not less than, but right, because it's cooling down a little bit more, right? 10 minutes, after 10 minutes, it's 100 degrees. So, I don't know, 10, 12, well, sorry, not 10, 12, 15, something like that, right? If I get 100 back, well, that doesn't feel great. If I get 6 back, that can't be right because it's cooling more, right? The temperatures drop more. Okay, so we have at least kind of a decent, check on whether the answer makes sense.
Wouldn't it be less than 10? It's already cool.